off with is Andrew from Northeastern, who will be telling us about ABI.
Thanks, Ben. Can everyone hear me if I stand here? This is like a good position? Okay. So this is joint work with Zach and Amal, who are both also here, although I don't know if they're both here, but they're both at Splash. So if there are any unresolved questions at the end, please come and find us. We'd love to chat. So today I'm going to tell you about our approach for the formal specification of ABIs. But before we dive in too deep, I want to just quickly establish a working definition for what an ABI is, since it's not something that most of us interact with on a daily basis. I really like this definition from the Swift team, which says that it's the runtime contract for using a particular API. And this includes the usual things like layout and calling conventions, but more broadly, it leaves the door open for specifying the expected behavior of an API, which is an important theme that we'll see throughout the talk. Just as a little example, suppose we want to compile a small functional type from a higher level language. We have a variety of implementation decisions ahead of us. The particular ones aren't so important here, right? But maybe we decide to splat the input pair or pass it indirectly as a pointer, or maybe we use a return pointer. The key thing about these choices is that whichever one we pick sort of precludes compatibility with the other one. And that really brings us to the main motivation for using an ABI, which is interoperability. The situation is this. Suppose that we start with two source-compatible components, which we're going to style in blue here. Ideally, compilation to two target components, we're going to style them in orange, should be compatible as well. And the subtlety is that even if this happens to be the case for a particular compiler, the story gets much murkier if we decide that we want to link with code from two different compilers. And this is a really big deal. I mean, imagine if you had to recompile every binary on your computer every time there was a GCC update. It would be chaos. Adhering to a consistent ABI is one of the things that allows compilers to update independently. But it's not just about compiler updates. Other languages will use the ABI to build foreign function interfaces, which enables interop across different languages. And for example, we've all probably used a CFFI at some point or another. And speaking of C, historically, it has been sort of the de facto standard ABI. But recently, there's been this renewed interest from systems languages in designing their own ABIs. And I think the real reason for this is that these are languages with richer types that have very particular invariants about ownership and safety. And there's been a lot of, I'll say, spirited discussion about how much of that actually belongs in an ABI. And I think there are a lot of open questions in these threads. And I think the community would really benefit from a formal analysis of the ABI design space. But that begs the question, how should we actually formally specify and reason about ABIs? Revisiting this Swift definition, a particular API for us will just be a type. And the runtime contract for using that type can be defined as a predicate on target programs that behave like or realize that type. And in fact, this is just an instance of semantic typing, which is a technique that we understand fairly well in the PL community. But more specifically, it's an instance of realistic realizability, which is this term that was coined by Benton to describe models that are indexed by source types and inhabited by real target code. For Benton, these realizability models were proof devices that he used during compiler verification. But our proposal is not to reinvent the wheel. We can actually take these models and use them as the definition of an ABI itself. In order to evaluate the suitability of this approach, we've conducted a case study in which we in which we specify the ABI for a simple functional source language that we compile to a C-like target. And because we were very much inspired by the Swift ABI, we approximate a small subset of its implementation features, most notably automatic reference counting. And to make this specification concise, we define our realizability model using a separation logic with some new abstractions for reasoning about manipulating reference counts. Now, before we dive into the particulars of the ABI for this case study, I want you to keep in mind that this is just one instance of the general methodology. So at each step, we should expect the ABI to address both layout and behavior. Since our values are reference counted, that's where we'll begin our tour through the ABI. Physically, a reference is just some pointer L. But logically, a reference for a type T is characterized by this predicate R, which says first of all, that L holds a reference counter, C here, And moreover, that in adjacent memory sits an object that behaves like a T. And this is characterized by the object relation O. Whereas the reference predicate is uniform in T, the object predicate will vary based on T. So for example, as a simple example, an integer, right? An integer object is just some integer that's sitting in a cell, and we represent this using the points to connective from separation logic. Now that we know the basics of how references are laid out, we must also specify how they behave. A single reference represents one share to the underlying object, and likewise, multiple references represents multiple shares to the underlying object. And this establishes a lower bound on the runtime value of the counter sitting at L. Now, having a reference count confers permission to increment the count and acquire more shares, which we specify here using this Hoare triple. Here it says, given a reference at L, incrementing L will not only increase the count, but it will also produce two references. And these are joined together using the separating conjunction, which indicates that they're two distinct shares to the same underlying object. Going in the other direction, having a reference also confers permission to decrement the count, but the protocol for doing so is slightly more involved. Dynamically, we might learn that the count is still positive, which means that somewhere else out there, there's another reference that we don't have access to. And in this case, we lose access to the underlying object, at least through the input reference, right? And that's indicated by this empty permission in the post condition. On the other hand, this might actually be the last reference, in which case we learn that the count will hit 0, and we take back full ownership of the cell holding the reference counter and the underlying object. And in this case, we assume the responsibility for managing that memory. Now that we have a sense for how references behave, let's look at another object interpretation, this time for simple functions. Physically, a function is just a pointer to some function f. But logically, it isn't just any function. It must adhere to the calling convention for the type t1 arrow t2. Here the convention is again specified using a Hoare triple, which says that we must move in a reference to the input in order to call the function, and upon return, we obtain a reference to the output. But this isn't the only calling convention one can imagine. Alternatively, you could insist that the function return a reference to the input as well as the output. The former would sort of be analogous to call or save, and the latter to call esave, but in this case, it's for references instead of registers. And both of these conventions end up getting used in practice. And separation logic is well suited for describing a variety of calling conventions, and we cover some more in the paper with additional features like recursion and closures. Now let's take a look at the object interpretation for structs. Physically, a struct just contains pointers to its fields, laid out adjacently in declaration order. So for this point example, it's x first and then y at offset 1. But logically, we know these aren't any old pointers. They're proper references to the fields. And remember that a reference holds a share to its object. And this, in turn, ensures that the fields live at least as long as the struct itself. Interestingly, this means that a struct may hold on to more memory logically than it does physically, since these field objects will live elsewhere in memory. To make this last point a little more clear, let's unfold the definition of R and rearrange things a little bit. So here we're grouping memory fragments by the object that they belong to. And in addition to these physical pointers that we had before, we're also using these thin gray edges to associate a reference with its object. Of course, the point object in the middle will most commonly be part of another reference itself, which may either be held by another object or by the root, as is the case in this diagram. Instead of using flat heap fragments, we use this graph representation to define the resources of our separation logic. More formally, we distinguish cells that hold reference counters from plain old data using these ghost tags, share and unique, where a share cell will contain the local share of the reference count and a logical edge to the object that it's counting. The advantage of using this representation is that it's really natural to define composition in a way that ensures that the total reference counts work out. For example, if we want to duplicate the point, we only increment the count at the root in a way that, and then the two objects between those two counters will have the same underlying memory. We don't duplicate the counts across the two of them. Likewise, if we want to duplicate a reachable reference like ly, we add the new reference to the root, and it points to the very same object as the original reference. Now, importantly, this is all just logical structure. The ghost tags are completely erased before we run any code. Resources that have this invariant, that the unique cells actually were unique, but the share cells will get collapsed and their reference counts will be added together. In order to reason about these graph structures, we use two modalities that are loosely inspired by hybrid logic. The first is this jump modality at LP, which says that L is a reference counter whose object satisfies P, and locally it also confers one share of the object. As we saw on the previous slide, composing jumps together only affects the local count, and it does not increment any of the internal counts inside reachable objects. And in fact, all the references that we saw so far are just defined in terms of jump and the object relation. And so all those properties about duplicating references are actually just properties of jump. We also use the more familiar reachability modality, diamond, which enables non-destructive operations like reading and incrementing from deeply nested objects. For example, let's revisit the increment rule that we saw earlier, which we redefine in terms of jump. Instead of references, we'll have jumps in each of these positions. Using diamond, we can generalize the rule to allow incrementing any reachable counter. Here, the premise says that the precondition queue, somewhere inside of the resource satisfying queue, we can reach a jump to P. And we duplicate that jump independently without affecting Q, and that's why Q appears in the post condition as well. Okay, let's backtrack a little bit and revisit the definition of structs. This is the same definition that you saw before. You don't need to reread it. There, we decided to lay out the fields in declaration order, which is similar more or less to the way that C does things. And there's nothing wrong with this definition, but this sort of rigidity does have some implications for the ABI. For one thing, seemingly equivalent source types aren't necessarily ABI compatible. Since we're using declaration order, we can't reorder fields even if that's a natural thing to do in the source language. Moreover, these structs aren't extensible. Imagine that you're maintaining a library over a long period of time and you want to add a new feature. This ABI wouldn't allow you to add new fields in service of that feature. Let's be a little bit more precise about what we mean when we say the ABI doesn't support these updates. The situation is this. Suppose that we have a library that's providing types to a client, and we know that the components are ABI compatible after compilation. The question is, what updates can we make to the library without breaking compatibility with the original client binary? If you've ever found yourself in DLL or dependency hell, that's exactly the situation we're trying to avoid here. Through the lens of a realizability model, we can characterize the ABI-compatible type updates using semantic subtyping. Informally, this means that the new type refines the layout and behavior of the original type, so it doesn't violate any of the client's assumptions. Now, whether or not the ABI actually supports any non-trivial updates is entirely a design decision. So C, for example, doesn't support any type updates of this flavor by default, so library developers have to design their APIs in a little bit more of a careful manner. Swift has a very different vision that it calls library evolution, and they support a variety of type updates by default. This is something that we formalize in the paper, but I just want to give you a sketch for exactly how the techniques works, at least as it was devised by Swift. At the heart of the technique is what Swift calls a resilient layout. And the key idea is that rather than fixing the offsets of a struct, the ABI requires that they be available in a table that clients can query dynamically. Here, the client may only assume that the layout is consistent with the offset table, but it makes no other assumptions about the remainder of the layout. Then when a library actually implements the type, it provides concrete values for the offsets, which may include more fields than the client is aware of, and in a totally different order. Crucially, the library internally does not need to use this offset table because it knows the layout statically. But across a linking boundary, clients need to use indirection, which allows flexibility between releases at the cost of some runtime overhead. In the paper, we show that our ABI supports evolution for a variety of types and that it guarantees safety and memory reclamation. We also show compliance for an ARC compiler, which is sort of like the fundamental property for a logical relation. We also cover unbox types and recursive closures, and we show how to express various type-directed layout optimizations that an ABI might want to support. For our next case study, we're currently looking at Rust, and we're working on an ABI with ownership and borrowing that we hope to define over WebAssembly. And the goal of this ABI is to verify an FFI, which is one important application of ABIs that we didn't cover for the case study in this paper. In summary, we've proposed a methodology for specifying ABIs using realistic realizability models, and we've exercised this methodology using a case study that introduces some new separation logic abstractions for reference counting. Thank you.
So we have time for questions. Just raise your hand, and George will bring you the microphone.
So in the hybrid logics I've seen, the thing next to the ads references a world. Is L a world in your semantics, or is it slightly different?
Yeah, so we're pretty careful in the paper to say that this is only a loose inspiration. It's world-ish in the sense that it does actually describe a node in the graph, and it does let you move between different nodes in the graph. But it isn't, formally speaking, a crypty structure, so it's sort of a loose inspiration, but it does have some relationship, yeah.
Well, I can ask a question. So,
Okay.
So this was inspired by Swift, and I guess you're looking at Rust next. Can you talk
Yes.
a little bit about what the complexities of working with Rust or integrating Rust ABI into the system are?
Yeah, so I mean, one of them is just figuring out what borrowing means formally, which there's been a lot of good work on, but I think there's room to go. Another interesting thing as it relates to Rust is that there's a bit of a debate about how much of the borrowing semantics actually belongs in the ABI. So there's this Krabby RFC, and they do have a notion of borrowing, or they have a notion of references, borrowed references in the ABI, but they don't have lifetimes, so it's not exactly the same kind of concept that we're actually familiar with working, using in Rust. So we're trying to sort of navigate that space. Does it need the exact same abstractions? Does it need weaker abstractions? And that's something that we're trying to figure out. Yeah.
Very interesting. We have time for one more question.
Thanks for the great talk and the really interesting paper. I'm curious.
Is this on? Okay. I'm curious. I think Rust doesn't really have a definition of an ABI for sure yet. Right? Yeah. Could you maybe use your work in some way to assess whether one definition or another would be a good idea given the way people want libraries to evolve in practice?
That's exactly what we want to do, yeah. So there is a proposal where right now it's just a discussion really about if Rust wants an ABI and what it might include. And our hope is that by analyzing these things formally, we can offer them, like, here are the trade-offs behind different ABI decisions, and then they can determine, what is right for them in practice. Yeah.
This sounds great. Thank you.
Yeah.